Hey guys, welcome to this particular lesson where we're going to be talking about how we're going to be working using this idea of Ethernet switching and how our concept of switches are going to be involved in our communication processes. So it's going to be really important for us to understand exactly what's happening with regard to how these switches are going to be interoperating with each other. Just give me 1 second here. I want to verify that I'm on the right console, and I am. And let's dive right in and see what it is we're going to be talking about in this lesson. Right now, what is important is for us to understand the fact that Ethernet LANs afford us different methods of connectivity. For instance, we have fiber optic connections, we have copper connections, we even have some of the old connections that we're going to see called coaxial connections. Now, as a general rule, coaxial connections have been pretty much outdated. However, there was a technology called twin-ax, which is going to be a coaxial connection with two conductors in the center. That's actually making a return as we start working with data center involvement and interconnectivities, because it gives us the capability of carrying high-speed information across short distances using copper as the primary tool that we can use to implement that. Now, also, we have to recognize the fact that when it comes to connecting up our devices, we have a wide variety of different options that we can choose from. For instance, we can choose from Category 5 copper cable, or as we see here over to my immediate left, we see that I have the copper or the fiber optic interconnections. Now, regardless of how we're going to be implementing it, it's still Ethernet. Whether it's electrical current or whether it's light, that's going to be the main idea, that it's still going to be Ethernet. Now, the main rationale behind using copper versus fiber optics, or fiber optics versus copper, is going to boil down to the overall distance, i.e. our fiber optics can carry information further than, say, our copper. But the other thing that we have to look at here is cost. Fiber optics is traditionally much more expensive than Category 5, Category 5E, or Cat 6 cabling. And we'll talk about those differences here in a minute. But really and truly, it just boils down to the idea of copper operating either as unshielded twisted pair or shielded twisted pair. And again, we'll get into the main benefits of that. But when we look at how this is going to be all interconnected, what we find here is that when we want to look at copper or at fiber, we are going to be working in tens of kilometers of distance. Now, when we start working with our Ethernet, it's going to be the idea of maybe up to 300 meters. So again, you can see the big difference between these two particular types of technology, but we have to embrace them. And the other thing that we're going to have to realize is that the majority of our Cisco devices that support fiber optic connections do it using something called an SFP, a small form factor pluggable module. It's going to be a small component that we can actually insert into our equipment, and depending on what type of SFP we have is going to determine whether or not we can connect fiber, the different types of fiber, or whether or not we can connect 1 gigabit speed Ethernet connections using copper unshielded twisted pair. All right, so with that being said, let's move on in our presentation. Now, the other element here is that, like I said, we would talk about this idea of shielded and unshielded twisted pair. Now, the main thing here is that what we can see, according to the illustration, let me grab a pen. Notice we have 2 wires, 2 wires, 2 wires, 2 wires, adding up to a total of 8 individual conductors, but each of those individual conductors are actually grouped in pairs of 2. Now, the thing that we need to recognize here is that we have this idea of twisting. So I'm going to take a pair, 2 individual wires, and I'm going to turn those, and it's going to be something like 22 rotations per inch. And then what we're going to find here is that's going to allow me to get rid of issues like inductance, things that can actually cause problems, because we have this concept that we need to talk about called RFI, radio frequency interference. Now, as I run Category 5 cabling, in most scenarios, it's going to be in the ceiling. Now, bear in mind, we have ballasts that are running our fluorescent lighting. We have motors that are going to be powering fans and ducts. So we need to make certain that we put these cables in specific locations where we're not going to be able to pick up radio frequency interference, RFI. Now, if we do pick it up or we can't bypass it, the whole idea here is that this twisting that I'm talking about reduces the impact of RFI, and it also reduces something called crosstalk. Now, crosstalk Crosstalk is important because what ends up happening is that, say, on this string of connections, I'm carrying a conversation. Now, what I want to do is I want to ensure that this conversation does not bleed over into any of the other pairs. This process is called crosstalk. So when we look at this, again, the twisting causes the RF radiation coming off of these cables, off of these individual wires inside of this cable. That's probably a more accurate way to describe it. Bear in mind that an individual copper conductor, if I'm running a signal through it, it allows the signal to go from point A to point B. But what we also have to understand is that it has the capacity of acting like an antenna. So in other words, it could actually broadcast the signal. We alleviate that process by using the concept of an insulator and also this idea of being able to do rotations or twists in our configuration. Now, another way that we could also do this would be something called shielded twisted pair, not UTP, but STP. STP actually goes so far as to inside the outer jacket, there's going to be a coaxial, not a coaxial, there's going to be a braid. That braid is going to be metal, and that braid is actually going to act as a shield. Now, where we do not have braid, what we're going to find is we have a foil wrapping. Makes the cable less heavy, makes the cable easier to manufacture, and costs less in the end run when we want to be able to acquire it and still get relatively the same amount of protection. However, there are environments like, for instance, in medical arenas where we actually positively have to have the braid in there such that it's going to be able to stop things like RFI coming from X-ray machines and things along those lines. So again, you're going to find yourself in a situation where you're going to be working with these, and all of these, whether they're shielded or unshielded twisted pair, are actually going to go to this style of connection right here. This is known as an RJ45 connector. Now, when we look at this, the main characteristics of UTP, unshielded twisted pair, is it's going to give me the support, the capability of doing 10 megabits per second all the way up to 10 gigabits per second. Now, keep in mind, this is also going to be restricted on distance. So the greater the throughput, the shorter the distance, which is one of the reasons that fiber optic cable becomes one of our possible requirements in the majority of deployments that are using Ethernet technologies, especially the further we want to go. The other part of this is that when it boils down to it, UTP is the least expensive solution that we can possibly employ. And the fact that it uses these RJ45 connections means that I have small form factor when it comes to putting these into things like patch panels and things along those lines. And the main goal here is the maximum cable length, again, is going to depend on the throughput capacity that we're going to have. Also bear in mind that inside of this cabling, inside of this individual cable, we have those two pairs of wires that are twisted, and those two pairs of wires are typically going to be a solid color and what's referred to as a striped color. So I'm going to have the idea of blue, blue-white. I'm going to have brown, brown-white. I'm going to have orange and orange-white, and then I'm going to have green and green-white, adding up to 8 conductors. Now, depending on how I want to be able to do my terminations, that's going to determine how I'm going to utilize those individual cables. And what we need to also recognize before we move on is the fact that we have different wiring standards. The first standard is going to be the one that we're going to run into the most, and that's going to be the 568B standard. We're also going to have 568A. Now, when we look at these standards, all it does is it's determining which pairs are going to be terminated where in this connector. Not necessarily something that we're going to need to know in the confines of preparing for the CCNA certification, but you will, in a real world scenario, want to know how that you can make different types of cables. The different type of cables that we're going to make are going to be a straight through cable or a crossover cable. A straight through cable is going to be a device that we're going to use to connect computers to switches or routers to switches. If I want to employ the connectivity between using two devices and I don't want to have a physical entity, like for instance, if I want to connect two routers together or two switches together, what I'm going to need is what's called a crossover cable, because what ends up happening is we're going to be using a pair for transmit and a pair for receive. Now, since they're going to be like devices, what I want to do is I want to rotate one end of the connection such that the transmit is going to go to the receive of the other connection and vice versa, going the other direction. That ensures the fact that I can use a crossover cable to provide communication between similar or like devices. Again, something that you're probably going to end up doing more often than not in the real world when you're doing testing. Now, another element to this is the connector itself. The RJ45 is a very, very small form module. It's about 1 centimeter in width. And you're going to see in most instances in any business, or even in some homes, an entire series of these connections. These connections, referred to as an RJ45 jack, are going to be how I'm going to connect cabling that exists in the infrastructure, in the walls of my building, to things like patch panels. If I want to take a computer and hook it up physically and not use radio transmission or RF, wireless technology, what I'm going to do is I'm going to use the cable like I have here. That cable is going to be simply plugged into this wall jack, and it's going to give me all the interconnection that I'm going to need to be able to move data from my physical location to a centralized point such that I'm going to be able to access the premises switches, desktop switches, or however I've got things implemented in my topology. Now, in other words, I could have a router in one closet connected to one of these wall jacks, and it could be going to a switch in another closet. And that's what we're going to have to understand. It all boils down to modular design and the fact that everything is going to be built typically in a physical star topology, but again, it's going to operate like a logical bus. Now, the other solution we have here is fiber optics. Now, fiber optics are not the end-all be-all. They're not the perfect solution. In fact, what we're going to find is we're going to have a concept called a macro bend. Now, when we start working with fiber optic cabling, we need to understand exactly how it's constructed so we can understand the significance of how we actually deploy it, what that significance is with regard to the impact. Now, looking at this, what we see here is we have two different types of fiber optic cable. We have multi-mode fiber, which is going to be used for transferring lots of individual signals and maintain the integrity of those signals over relatively moderate distances. We have a single mode fiber, which is going to carry one signal. So multi meaning more than one signal, single mode meaning I'm only going to be able to carry one. And look at the operational differences. My multi-mode fiber has a fiber optic conductor that is 50 micrometers in width. My single mode has a 9 micrometer thickness. So the multi-mode is bigger, and we're going to understand why when we start looking at how this is implemented. The other thing that I want to point out here is notice that we also have an insulator. The insulator in the confines of our fiber optic cabling is referred to as cladding. So if we notice here, we have a width of cladding that is going to be much less than the width of cladding in, say, a single mode fiber connection. Now, bear in mind, single mode can carry one signal, but it can carry that one signal significantly further than, say, multi-mode can carry its multiple signals. Again, we only have one signal. We don't have to worry about maintaining discrete or integral differences between each of our different traffic flows. Therefore, multi-mode is going to carry more information. It's going to be more commonly used. But if we need to shoot a signal across a greater distance, say tens of kilometers, like I said, or greater, then what we're going to end up doing is we're going to end up using single mode fibering. Now, when we start looking at this, it's really important for us to understand, like I said, we have this concept of macro bends. Now, when I deploy fiber optic cable, it's important for us to understand how the signal goes through. So as we see here, I have two different types of cabling. I have directly right here, single mode, and on this side, I have multi-mode. Now, each of these black lines that we see traversing, let me go ahead and grab a highlighter. Each of these black lines that we see traversing the signal or traversing the media is a different data flow. Notice, multi-mode carries multiple flows. Let me grab another pin here. So here we have two flows, where in the single mode, like I said, we only have the one flow, and it travels through the core. Now, in copper, at high frequency, there's something called skin effect. And it's not really part of our conversations, but it's important for us to understand that. But in fiber optic connection, we actually travel or send our signal, either our LED indicators or our laser light is going to actually travel through the conductor. Now, the reason that I have a wider core, let me grab an actual pin here. The reason that I have a wider core in the confines of multi-mode is so that I can employ something called reflection. Notice that each of these two signals that I'm moving through this infrastructure, the pink one and the green one, are hitting the outer core, between the core and the cladding, and they're reflecting back at different angles. This allows me to say, okay, well, I'm going to shoot one through the fiber at a greater angle, which means I'm going to have more impacts than, say, one that is at a less or acute angle, like this pink one. And by virtue of the fact that that signal is bouncing off the cladding, it's actually bouncing off the outer ring or the outer surface of the core, which is between the core and the cladding. So it's going through, and I can actually bounce multiple signals. Now, there's no requirement for that when we start looking at single mode fiber. So in other words, I can have a smaller conductor, therefore I'm losing less light because I have less reflection going on against the outside of the core. But when we start looking at it, I can shoot greater distances using multi-mode. Also the fact that I'm only carrying the one signal type. Now, what I want you to recognize here is that we have this glass core. Think of it like a long extruded glass tube. And the outside of that is polished, such that as signals do go through, even in single mode, they're still bouncing, as you can see, off of the core, the outside of that ring, because it's reflective. But it's also because it's wrapped by the cladding. Now, the cladding is fibrous. The cladding looks almost like little superfine microfibers that are wrapped around the glass in order to be able to protect it. Now, the problem is when we start looking at how we deploy it and we do bends, say, for instance, I need to turn an angle inside my infrastructure. What I'm going to find is these angles, whether depending on how great or how acute the angle is going to directly impact how the signal can go through. Now, I'm going to highlight it right now before we talk about these connectors, but I also do have part of my presentation that's going to discuss it. Imagine that I'm looking for something that I could physically use. I don't have anything. But imagine that this pin is my fiber optic cable. This is the actual core. So the light is traveling through this pin. Now, if I take this pin and I bend it at greater than a 90-degree angle and at a radius that's less than 30 millimeters, what ends up happening is the cladding, which is that microfiber that's wrapped around the core, gets pushed up against the core itself if the core doesn't break. And what happens is it actually separates those fibers a little bit to where what happens now is that my bend is so great that light can escape. The light comes in, hits the corner and starts shining through, and then what ends up happening is I get degraded signal on the other end. So think of it almost like the light is being leaked out because when I bend it, I place the cladding under strain. That's something that we definitely want to make certain that we avoid. Now, the other scenario here is going to be the fact that we need to pay attention to the style of connections that we're going to be working with. Inside the confines of the majority of my deployments, I have worked with regular ST connections, I've worked with SC, and I've worked with LC. Now, the really cool part about these two is the fact that 90% of the time, notice that these square containers or these square connectors, they're polarized. Now, what do I mean by that? I mean, we can only put them in a particular connection at a time, and we can't change or alter their orientation. So by polarizing the connections, what we do is we make it simpler to avoid situations where we hook the cables up improperly. Remember, we're going to have a receive side and a transmit side. So if I'm transmitting, I need to put that signal into the receive side. In other connections, like these ST connections, what ends up happening is a lot of times you get these flipped. Now, the way we avoid that is our SC and our LC connectors all go into a little module that slides in at one time. And since it's polarized, the orientation is significant, so it's only going to go in one way. So as long as we set the modules up properly, we've minimized the probability of being able to induce situations where we're not going to be able to send signals from point A to point B. So by flipping it. And miswiring fiber optic connections is definitely one of the main issues that we're going to run into time and time again when we go in and we start working with fiber optic connections. Because remember, we have to have one strand for transmit, one strand for receive. In our copper connections, all of that is integrated into one individual plug, and so long as the connector, the RJ45 connector, has been applied properly and crimped correctly, we don't have any issues with regard to messing up our connection. Now, the other part of this is that we need to understand, like I said, at layer 2 in our model, in our deployment model, whether we're using the OSI model or we're using the TCP IP model, is irrelevant because at layer 2, at the link layer in the TCP IP model, or in the data link layer in the OSI model, we're communicating using frames. Now these frames are significant because what we're going to find here is this is going to include all of the information that we're going to be extending through our connection. Now this is going to be typical of what we call the header. So this is my layer 2 header. Now, a layer 2 header is very significant because the layer 2 header defines where the packet or frame is coming from and where it's going to. Notice I have a destination address and I have a source address. In the confines of Ethernet, these addresses are MAC addresses. Now, we also have the actual data. We have the file checksum configuration that we're talking about. I'll move out of the way here and point out this is the data, this is the actual payload, and that payload can be anywhere from 46 up to 1,500 bytes in size. But the thing we need to recognize here is what's called the preamble, which is basically the introduction, is going to be a fixed range of 8 bytes. The MAC address is going to be 6 bytes of information, which is going to add up to 48 bits. As well as 6 bytes and 48 bits for the source address. So in other words, in this header is everything that I need to know to work at layer 2. I've got the payload. I've got the file checksum that I'm going to use on the other side to see if anything happened to the frame as it traversed my infrastructure. I have where I'm coming from. So when the other end responds, it's going to use the source as the destination on the other side. And that's how we're going to create this concept of bidirectional communication in our infrastructure. Something that is exceedingly important and we cannot afford to take for granted. But just like we were talking about earlier on, remember I said there are different types of communication. We have unicast communication, we have broadcast communication, and we have multicast communication. The best way to be able to outline that, and I'm going to grab a different pen color, is when we look at this, unicast is going to be the idea of one-to-one communication. So I'm going to have one device talking to an individual other device. So in this instance where this is A, I want to talk to C. So this is A, B, C, and D. Host A, host B, host C, host D. Now when I send a unicast communication, it's going to travel and it's going to go between the source to the destination. Now when we look at this, I also mentioned the fact that we also have what we call one-to-all. So I'm going to say one-to-all. One-to-all defines the characteristic of broadcast communication. That means I can actually send out a frame that's going to go to every device in my infrastructure that's on that network segment. Now keep in mind, that defines a broadcast domain. We talked about the fact that switches break up collision domains, but they do not break up broadcast domains. We need a router to break up a broadcast domain because a router is going to be the device that sits between multiple networks. And if I have 2 different networks, there's no instance that I can even possibly think of where I would want to make certain that a broadcast packet or a broadcast frame jumped to another network, because that broadcast is only intended for all of the devices that are on my network when I send it. And what we need to recognize is here, that means that signal, I'll go ahead and grab a different pin color here, is going to go from A, B, C, and D. And what we're going to see here is that signal is actually going to go to each of these individual devices, both B, C, and D. Now, the other solution that we were talking about was multicast. Now, multicast was really significant because multicast changes the rules. What we're going to have is we're going to have a group address. We'll talk about the idea of multicast addresses in the second part of our IC&D discussions. But what we need to realize here is this multicast address is kind of like tuning to a radio frequency. So I mean, in the Army, we used to have these things called guard receivers. So we'd be out in the field, and you'd turn this little teeny tiny radio to the guard band receiver, and if any emergency happened, or we would receive instructions either to implement the mission, change the mission, bug out, any of those things, everyone had the radio tuned to that frequency. So all that had to happen was the command tent would come on, and he would say, you know, bug out or change a fire mission or whatever. Now, the same thing goes with this idea of a multicast group address. This group address means anyone who is listening to that group address is going to receive the messages. In the context of sending information, what we're going to find here is that in this instance, if A is generating that information, so it's sending it to that group address. So it's to the group address. Any device that's listening to the group address has the capability of hearing it simultaneously. So in this instance, C and D are group members, which means they're actually configured to listen to that address, which means when that information or that frame arrives, they're going to process it. The scenario, or the main difference is that between broadcast, let me change pins again, between broadcast and multicast, we have one key difference. And that is that in a broadcast environment, everyone's going to receive the message. Whether they want to get it or not, they're still going to receive the frame. They're going to have to drop it. The idea here is that in the context of our multicast scenarios, only the devices that are actively listening to the group are going to receive the frame. Therefore, multicast is far more efficient and less bandwidth intensive than, say, our broadcast scenarios. So again, that boils down to ensuring that we understand the nature of our header and the format that the signal or the communication is going to take as it goes through. Now, the other part of this that we were talking about was the idea or the nature of MAC addresses. And I'm just going to simply illustrate this again, this one more time as we go through. Because what we need to recognize, like I said, MAC addresses are 48 bits. They take the format of 3 groups of 4 hexadecimal characters. So it could be 1, 2, 3, 4, .A, B, C, D, .5, 6, 7, and 8. Now, the key thing that we need to understand here is that of these values, like I mentioned, the first set of numbers are actually corresponding to what we refer to as the organizational unique identifier. The OUI tells me who made this device. The second part of this really just translates to the idea of a serialization value. So what will end up happening is that if this 123.AB was Cisco, 9 times out of 10, the remaining values, the next 24 bits, are going to be the serial. So for instance, it might be, 00.0012. And that could be indicative of which particular, or what it was in this scenario, it's not 12. Let's use a value that I can work with here, like 0. So that too tells me that's the second network card that was produced. If it was going to be F, it would tell me that it was the 16th card that was produced. Bearing in mind 0 is still a significant digit because we're counting concatenately, which means we're counting from 0. So all of our first values are always going to be 0. Now, recognizing the fact that this number must be unique in our infrastructure, and the fact that it is unique allows me to use it as my source and my destinations for all of my frames that I'm going to be sending throughout the network. Now, the other part of this also is that we still have that idea of our logical addresses and our physical addresses. Now, bear in mind, physical addresses are sometimes referred to as BIAs, burned-in addresses, and those are our MAC addresses. Now, when we start looking at how this is all interconnected, it makes sense, but remember, we use this for the actual sending of frames across our wire, which means we have to know the source and destination MAC addresses. But we don't always know the destination MAC address. We know our source, obviously, because it's hardwired to our component, but we don't necessarily know about the destination's MAC address. Now remember, in that illustration where I came into the business and we had the server and our computer and Bob's computer, how did I know how to get to the server? Well, I had the server's logical address, which is typically an IP address. V4, V6 is irrelevant to our conversations. But what I need before I can actually encapsulate a frame and send it on the wire is the destination MAC address. And what we use is another solution that we discussed loosely called ARP. Address Resolution Protocol, where I take a MAC address and I have a series of processes that I follow in order to be able to obtain I have the logical address, and I can use ARP to find the physical address, the burned-in address of my destination. And what we're going to need to do is understand exactly what components in our infrastructure are involved in that process and how they operate and how they're interconnected. Now, when we work with these MACs, the whole idea here is like I said, the fact that we're using these to identify specifically the source and the destination. Now, bear in mind, each of these components, say the source is a host, the destination is another host. Bear in mind that each of these have a network interface card. that's going to be physically connected across whatever media we use, whether it's going to be Ethernet copper or Ethernet fiber is irrelevant. It's still Ethernet, which means the frame style that I illustrated is what we're going to be sending across the link, irregardless of the media type, fiber or copper. Now looking at this, each of these network cards have MAC addresses that were assigned to them. Now, when I look at this, I mean, what's the possibility or the odds that in a live environment I'm going to have one host connected directly to another host? Slim to none. So what we have to recognize here is that more often than not, in here, somewhere, we're going to have a switch or a series of switches. This meaning that what I'm just describing right here is a logical diagram. The physical diagram would include any switches that may be in the connection, as well as any physical interconnections that are running between devices and switches. So in other words, this could be simply two cables, not just one, or it could be three cables if I had two switches. So I'd have to connect one device to a switch, another switch to another switch, and then another switch to the other device. So it would be three cables. But bear in mind, that's the fundamental difference. Cisco wants us to understand the difference between physical topologies, physical drawings, and the idea of a logical drawing. More often than not, you're going to see, especially in CCNP, you're going to see logical drawings because they're going to want you to know and understand how to actually define what's connected to what. And we're going to discuss a protocol that's going to make that perfectly capable or easy for us to use called CDP very shortly. It's referred to as Cisco Discovery Protocol. In fact, it works so well that the industry standards body created something called LLDP. That's going to be Link Local DP, Link Local Discovery Protocol, LLDP. Link Local Discovery Protocol, which basically just completely ripped off CDP's operation and function. They're not compatible, but they do the exact same thing. And it's going to be a primary tool that we're going to use to discover exactly what's happening in our infrastructure on a case-by-case basis. Now, I've done quite a bit of talking about how this process takes place. And what I want to do is I want to walk through the intercommunication of exactly what's happening. Now notice, in each of these illustrations, I have the switch. Now what I'm going to do is I'm going to look at how the switch is involved in this basic operation. This is going to be the same network across the next series of presentations. We're going to be talking about the same network, but we're going to look at it step by step by step. And we're going to discover exactly what's happening. So the idea is, in this deployment right here, I have this device, A, B, and C. So I'm going to draw it in here for each of them. Now I have a frame that I want to send. And that frame is really significant because I need it to go somewhere. So let's say that I want it to reach C, ultimately. Now, when I go through here, I'm going to send this frame to my switch. And the switch is going to say, I need to send this to a particular device. I am coming from PCA. So it sees that as my source. So what will happen is this switch is going to modify its MAC address table to include my source MAC address. But the problem is that nowhere in this table do I see an entry that tells me anything about this device right here. So what's going to happen is the switch is going to wake up and it's going to say, well, I need to follow some rules. The rule that I'm going to follow is that I'm going to flood this frame. I'm going to send this frame out this link and any other links that I have connected to me, but I'm not going to send it out the link that it came in on. Again, a loop avoidance mechanism. We'll talk about the exact idea and the process, but what's going to end up happening is what we see here. Notice this is telling me it took the frame that I sent in to the switch, and now it's sending that exact same frame down to each of these devices. The problem is I want to talk to PC, in this scenario, C, this particular device. And I don't know if this is actually going to marry up, but we'll make it. So the idea is that I don't want to talk to this guy, but I do want to talk to this guy. So in order to make this happen, what I'm going to do is I'm going to do that flooding. So the flooding is going to send the information out each of these links. And what will happen is it'll arrive here and it's going to say, well, I don't have that address. So that's not me. So what it's going to do is it's going to take this frame and it's going to put it in the bit bucket. It's going to just dump it in the garbage. Well, the thing here is this device connected to port 3 is going to say, oh yeah, that's me. And the moment it says that's me, it's now going to reply to that message. So it's going to say, oh yeah, that's me, and that frame is actually destined for me. So let's look at that process. Now that that's been done, and I've recognized that I am now this device. So again, let's put our labels in here. So A, B, C. I'm just using this to keep everything separate. Now notice this device said, oh yes, that was me. So I'm going to respond to that frame, that broadcast frame. Because what's happening is that it sees this and it says, I want to connect to a device. The switch is going to apply the address on port 1 as the MAC address of this computer. Let's just say it's A. We'll just keep that same thing. Now what's going to end up happening here is this device, like I said, is going to send that frame back to the switch. And what's going to happen is the switch is going to update its CAM table, its Content Addressable Memory Table, or sometimes referred to as the MAC address table, with the MAC address of this computer. Let's say this computer is B. So as you can see right here, it says on port 3, I'm connected to MAC address B. And then what it's going to do is it's going to send that frame to A saying, hey, I found him, and this is who he is. So now what we have is we have a populated CAM table that says, okay, I now know where both of these devices are. So now what we need to do is entertain exactly what's going to happen in the connection. So once that goes into place, then we can bring up our link. I now know how to get to that device, so now I'm going to send unicast flows to it. Now what we want to talk about now is what governs how we can send information across those Ethernet links. Now remember, earlier in our conversations, I alluded to the fact that we have this concept of duplex, full duplex, simplex, something called half duplex. And what I want to do is I want to highlight those because that's going to govern how we're going to use our links on these switches. Remember, I mentioned the fact that a switch operating in full duplex has the capability of absorbing collisions. Therefore, we don't have that concept of CSMA CD, Carrier Sense Multi-Access Collision Detection. We avoid it in the first place without going as far as passing tokens like in the CSMA CA, Collision Avoidance Method. Now, that all boils down to how we're going to communicate and how we're configured to operate. And what we want to do right now is highlight the fact that we have different modes of operation, and it extends to duplex. Principally, we have two modes. We have half and full. To get the full benefits of our switches and absorbing collisions, we need full duplex communications. Now, recognizing that, we also have to realize the fact that as we go through and we're working with all of these different components, this is going to define how data is moving through our infrastructure. Notice I just have one arrow with one end on it, and that's defining a unidirectional data flow. Now the problem is that without full duplex, I have no buffer. So I can't absorb frames, which means I have a higher possibility for collisions. Now this is referred to as a legacy connection method. It's not normal for us to have this type of infrastructure now, but definitely in the day when I was coming up, it was not only possible, it was a problem. Now, how do we avoid that problem? We'll avoid that problem through the concept of full duplex. Full duplex operation means exactly what it implies. Now I don't have a one-directional data flow, I have two-directional data flows, and in order to be able to do that, I actually am employing a concept of a buffer. So now I'm operating as a full-blown switch. The majority of our half-duplex configurations were back when we had a lot of hubs or concentrators in our infrastructure. Switches are completely different. The idea here is that we have to have point-to-point connectivity. Now what does that mean? Well, that means if I had a hub connected in this infrastructure that was connected to this switch and I had 3 computers on it, I could not run full duplex on this link. But unfortunately for all of us, this entire methodology has normally gone by the way of the dodo. The only time that I've ever really personally employed hubs in today's networks is if I want a device where I can just break into an Ethernet segment and do some sniffing without having to set up something like ER span or span configuration. And we'll talk about those definitely in the confines of CCNP. Now, again, like I said, the points have to be point-to-point, which means I can only have 2 devices, 1 device on each end, because if I'm going to use this idea of a buffer, I need to know what it is I'm buffering, and unless I can delineate, I can't do that. So I have only the capability of supporting 1 device on each end of the connection. Now, that device could lead to other destinations, but so long as the individual link is going to be a point-to-point connection, that's all that matters. So this connection must be point-to-point. This connection must be point-to-point. By virtue of the fact that they're point-to-point, I get buffering capability, which means I can support this idea of bidirectional flow. Now, the thing is we have to support full duplex on both sides. That means I need to make certain that I have the same capabilities on both sides of the link. So if I have 100 megabit on one connection and 10 megabit on the other, if I want to support the concept of full duplex, that means I'm going to have to go down to my slowest speed as my full duplex operation. So think of it almost like if I have a 100 megabit connection, that means I can send and receive at 100 megabit if I'm in full duplex. However, if I'm at 100 megabit connecting to a 10 megabit, then the fastest that I can send and receive information based on the slowest end of the link is going to be the 10, so it's going to be roughly like 20 megabits of throughput. I mean, that's an oversimplification, but it's still a very good way to be able to look at it with regard to how things are operating. So when we start looking at here, this idea of duplex introduces a series of possible problems. Because remember, I said that our duplex has to match. By default, the majority of our interfaces are going to have a mode of duplex auto, which means we're going to use some type of communication between our different components in order to be able to negotiate a speed. It's going to use an Ethernet process referred to as link pulses. Now, these pulses that we're going to be sending are going to be electrical signals that are going to travel between devices. Based on the information that's going to be part of those, the systems can negotiate connection. It is recommended in most scenarios that we hardwire or hard code duplex operation and speed. Because remember, if I have 10 megabits on one side, bear with me one moment. If I have 10 megabits on one side and 100 megabits on the other, my speeds need to match before I can operate in full duplex. And the commands that we're going to have here, like I said, are going to be duplex full and duplex half. Those are the 2 primary commands that we're going to see implementing here. We also, more often than not, are going to want to hardwire the actual speed. Now, by default, notice we have 2 different configurations here. Fast Ethernet 01 can have full, completely different configuration settings than, say, Fast Ethernet 05. By default, both the speed and the duplex are going to be auto. So when we go through here, what we need to realize is that means we're going to have a situation here. So let's see. General recommendations. Use manual settings on infrastructure links. What's an infrastructure link? Well, that's going to be a link connecting to switches or to routers. Also, use auto settings when we're going to go towards end devices. So it's perfectly fine to use auto negotiation to connect to a host, but if I want to connect between 2 switches, Cisco recommends that we actually go so far as to set these up as manual configuration. So in other words, we want to set them up to where they are not going to renegotiate. Now, what's the logic in that? Well, the logic is if switch 2 and switch 1 in this scenario, just for some reason, decide that they want to renegotiate that link during the period of time that it takes them to renegotiate the speed, say for instance they want to move to 10 megabit or 100 megabit, what will end up happening is we're not going to be able to send information through that link itself, which means we're going to be directly impacting the performance of our network, something that we want to avoid when and where possible. Bear in mind, between this host and this switch, if something happens and we go into a renegotiation, it's only going to affect this host and its connection to its switch, whereby a problem here is not going to impact other traffic. Imagine that we have 50 different computers connected to each of these 2 switches. It's going to be that link between them, what we'll learn later on is going to be called a trunk, that's going to allow us to carry all of their information. So if something happens to that infrastructure link, we can find ourselves looking at scenarios where we have a loss of data throughput in our infrastructure that can be problematic or catastrophic. So as we go in and we start looking at things, the main option here is to understand the fact that we have a interactive model. So here's the situation. I'm going to have duplex settings on each end of my link. let's use this table to explore exactly what's going to happen in these different configurations. I'm going to grab a pen and I'm going to highlight where we lose data. Anywhere it says mismatch, we're not going to be able to actually negotiate. So if I have full and I'm running half, they're not going to be able to negotiate. The reverse of that scenario is if I'm running half on this end and full on the other, it's the exact same situation. So that's not going to necessarily be anything that we want to entertain. So that's going to be something that we're obviously going to see because, quite frankly, no data is going to be moving through our infrastructure if we have a mismatch of full and half on either end. However, what we want to be aware of is what's going to happen when we have a mismatch, but we have the capability of employing negotiation, or we're going to see the fact that we're going to have degraded operation. Degraded operation can be almost as bad as the idea of being able to have this whole concept of a mismatch. So if I have auto and half, I'm going to negotiate half. That makes sense. If I have auto and full, I'm going to negotiate full. If I have auto and auto, it's going to try to go to the highest speed possible. But what happens if I have half and auto? It's going to negotiate half, whereby I may have thought that I'm going to go up to like 100 meg. So that's going to be definitely an issue. So when we look at this, the main thing that I'm asking you guys to understand is that auto is going to negotiate whatever the other side says if it's hardwired. So if it's auto and full, it's going to be full. If it's auto and half, it's going to be half. If it's auto and auto, it's going to try to negotiate at the fastest speeds possible. If it's hardwired for half on one end and full on the other, it's going to be a mismatch and we're not going to move data across this link. And that's going to be a main point. Now, duplex isn't the only scenario that we need to be concerned with. We also want to pay attention to concepts like speed. But if I want to see exactly what's happening, notice I have the capability of doing show interfaces. I can specify the interface. This is on a switch command. And notice right here, it tells me what my duplex is. It even goes so far as to tell me what my media type is. This tells me I'm using a UTP copper connection, 10 base 100 or 10 100 base TX. Now when we look at this, this is pretty handy because it allows me to execute a show command on the device in order to be able to see exactly what its operational mode is. Now, keeping in mind that each of these different components can impact us with regard to troubleshooting, we need to just step back for a minute, kind of let this sink in, and understand exactly what's going to happen if we do a manual configuration, recognizing the danger that if we do it and it's not matching on either end, we're not going to have our link up and operational. But bear in mind, auto negotiation is going to only give us full throughput if it's auto on both sides, or if we remember to say full on the other. So when it comes to negotiating this duplex process, we need to be aware of what is going to be happening when we implement the commands. And like I said, Cisco is telling us that they want us to implement the commands on our infrastructure links. That is going to be links that by definition are going to be connecting between, say, switches and routers or multiple switches. At the end host, we can go ahead and leave it on auto based on their recommendation. I have seen deployments where they leave it on auto everywhere because, I mean, let's face it, what's the actual issue of the switches coming along and deciding that they want to change from full duplex to half duplex out of the box? It would take a requirement or a problem on the link. It could be induced by an actual cabling failure, but they're few and far between in an actual live environment. However, keep in mind, Cisco does recommend that we actually do it and we set it up manually on these infrastructure links, which means we have to be aware of the fact that we can, by accident, hamstring or create a bottleneck in our infrastructure because we're not actually negotiating the best possible speed and the best possible duplex operation. So with that being said, what we're going to do is we're going to dive out of this particular lesson and we'll move into another lesson where we're going to be talking about other components, and then ultimately what I'm going to do is I'm going to move into a concept where we're going to be discussing troubleshooting. I'll see you guys in the next video. Bye-bye.